So hello to everyone who's watching on YouTube. So I'm waiting for I'll wait for 2-3 minutes so that a few people may join the meeting. So yeah, so I'll start in 3-4 minutes to everyone who's watching on YouTube. So yeah. Okay, so I guess since no one has joined the session till now, I'll just get started then. So, to hello to everyone who is watching on YouTube. Just to reintroduce myself, I'm Lakshay Saggi, the discrete maths TA for the Tuesday sessions, and this is the 11th session now. And in this session, I'll be discussing problems related to group theory. So yeah, so groups and some group subgroups. So yeah, very basic problems related to groups, which were like the concepts which were discussed in the in this week of NPTEL course. So yeah. So I have a bunch of problems, and I'll just maybe get started with the problem. So I'll just share my screen, and yeah, we can get started with the problems then. So yeah, I'll just share my screen now. So yeah, yeah. So I hope my screen is visible to everyone. So yeah, so I'll just get started. So as I discussed, like this week's problems are on group theory. So like I usually do in the problem solving sessions, first I would like maybe you guys would have already watched the lectures, but still like I like to start off with some preliminaries. So people who may have missed some concept or may have some doubt may get it cleared up here itself while watching this problem solving session itself. So yeah, so maybe I'll just get started with some preliminaries then. So, first of all, like I'd like to start off with defining what a group is actually. So, yeah. Wait. So, first of all, like we need to understand like what is a group. So, what's a group? Basically, a group is nothing but just a collection of a set G, where this G is a set of elements, and there's an operation O, such that this operation is over the set of elements G. So basically, a group G comma O is essentially a set G of elements with the operation O defined over these elements. And note that any set and any set and an operation will not constitute a group. So we'll call it a group. We'll call this pair a G comma O a group only if it satisfies some properties. And what are the properties? So there are essentially four properties for being called a group. So I'll discuss what are these four properties. So a group is essentially a set of elements with the operation O defined over these elements such that the following four properties hold. So if these four properties which I'll mention hold, then we'll say that this G comma O is actually a forms a group. So yeah. So the first property is closure. So what this means is that for any two elements A comma B in G, so if we define any if we take any two elements A comma B of G, so there can be multiple elements in the, so G is essentially a set of elements, right? So we can take any two elements of that set G, uh, then AOB, then this value. So AO operation is essentially defined over, so this O is an operation, right? So O needs two operands. So if A and B are the operands for this operation, uh, then what essentially we are saying in this closure property for any two elements A comma B in G, this value. So O is an operation, so it takes in two operands and gives one output. So basically this value AOB should also belong to G. So this is what you call the closure property of the group. That if we take any two elements of the group and we just do the operation O, which is defined, then the AOB value should also belong to that group G. So this AOB is an element, and that element should also be a part of this set G. Then we'll say this has the closure property. The second property which we need for G comma O to be a group is associativity. So what is associativity? Associativity is a property which we learn in high school also. So what does associativity mean? For any three elements, so G is a set of elements. So if we take any three elements, A, comma B, comma C in G, so note that these A, B, C, and here this A, comma B need not be distinct. Like this A, comma B can be equal to each other also. Here also, A, comma B, comma C can be equal to each other also. So there is no distinct elements written. These are just any three elements we take from G. So if we take any three elements A, B, C from G, then the value of A, O, B, O, C should be actually equal to if we compute AOB first and then uh, do it with C. So yeah. So what does associativity mean? So associativity just means that if we are given three elements, then uh, like the order in which we do the computation does not matter. Whether we calculate BOC first and then calculate A of BOC, or if we take AOB first and then take AOB of C. So I like to think of it as something like a matrix multiplication type stuff. So in matrix multiplication also, if we have three matrices A, comma B, comma C, then we know that if we multiply B and C first, we'll obtain the value BC. And if we multiply that with the matrix A, then we'll obtain the then the matrix final matrix obtained will actually be equal to if we first multiply the matrices A and B and then multiply that matrix by C. So yeah. So this is what you call the associativity, and like this property should also hold in a group. And then what's the third property which should hold is existence of an identity element. So so what does an identity element mean? So there should what this means that like we know, like let's just see what identity element is intuitively. So before writing the definition, so we know, like we have learned in high school in lower classes, that zero is the additive identity, one is the multiplicative identity. What does that mean? That in to any element, if we add zero, then the result stays the same. Similarly, if we multiply any element by one, the result stays the same. So here addition and multiplication are the operations, and like the group, the set of elements is the set of, let's say, natural numbers, real numbers, or anything. So yeah. So basically, what an identity element is an element. Uh, if we do, like, basically for any element of the group, if we multiply it by an identity element, or let's say the specific operation which we have here, if we do the operation with that element, the output should still be the initial number which we do, the initial element which we do. Maybe I should write this to get a better understanding. So there exists, so there should exist an element E in G such that for any element A in G, uh, the value of AOE should be equal to the value of EOA, and this should actually be equal to A itself. So, uh, so this is what you call the then E should be called, then E would be called the identity element here. The identity element of the group. So yeah. So this is uh, this is the property of existence of an identity element. And note that basically if this O was actually multiplication, and like this E was actually, let's say, 1, then we are sort of, then we can see why 1 is the multiplicative identity. So basically 1 is the identity of where if the operation is multiplication and this group is, let's say, the group of real numbers, because then this number A multiplied by 1 will actually be equal to A itself, and it will also be equal to 1 times A. So yeah, so I hope you get the intuition of what an identity element is. And so note that why did I write this AOE and EOA separately here? Because for any two elements, let's say A and B, it is not necessary that the value of AOB and BOA should be equal. We have not stated it anywhere. So a group need not satisfy this property that AOB should be equal to BOA. This is called the commutative property. Addition and multiplication do follow this property, but over like, let's say, real numbers. But these properties are not necessary for something to be called a group. So yeah, so note that this AOB value and BOA value might be different from each other. Like we have studied in matrix multiplication in high school that commutative property like matrix A times matrix B is not equal to matrix B times matrix A in many instances. So yeah, so just keep this in mind that AOB and BOA might be different. And what's the last property? We had said that four properties should hold for something to be called a group. So yeah, I would also like to point out first of all that uh, the order here which we have defined. So there should exist an element E. So first we said that there should exist an element E, and this E is now fixed. And now for any element A in G, this specific E which we first picked should have this property that AOE should be equal to EOA, which should be equal to A. So note that we can't choose E differently for different A's. Like for two elements of G, this E should be the same. Like we can't say with this, like let's say we take two elements A and B, we can't say that E1 is the identity with respect to A if like A times E1 is equal to E1 times A, and let's say B times E2 is equal to E2 times B. Uh, then we won't say that E1 and E2 are the identities. Like we first pick this element E, and then this element E should satisfy this property for all elements A and G. So note the order in which I have defined this. So there should exist an element E in G which satisfies everything. So yeah. So this is something which I want to point out. And then what is the last property? Existence of inverse, or let's say invertibility. So what does invertibility mean? So like we know that we know what like in what are additive inverses and what are multiplicative inverses, right? Like for a real number x, its additive inverse is 1 by x minus x, and its multiplicative inverse is 1 by x. So similarly, now we generalize this sort of argument to groups, this sort of definition to these groups. And what do we call invertibility? So for any element A in G, or maybe let's say, yeah, for any element A in G, there should exist an element B in G. So B should also be a part of the group G itself, such that AOB should be equal to BOA, which should be equal to E, where E is the identity of the group. Or let's say identity element of the group. Yeah. So so note that what are we trying to say here? So here we are saying that for any element A in G, there should exist an element B in G, such that AOB should be equal to BOA, which should be equal to E. So one thing to note here is this, like this, obviously this B will now be different for the choices of A. Like if we choose some one A1 and second A2, then the B corresponding B's will be different. That's how we define it here. Like for any element A in G, there should exist an element B in G. So yeah. So this B will depend on the A we choose. Like in, let's say, in addition, what we do is for any X, like for finding additive inverse, what we say is for an element X, its additive inverse is actually minus X. So as X changes, the value of minus X also changes. So that's what I want to point out, that this, so if A is X here, then B would be minus X if we are strictly talking about addition. So that's what I want to point out, that this B will change according to the A what we choose. But this E is fixed, which is the identity element of the group. So yeah. So mm, so this B is called the inverse of the inverse of element A. Inverse of the element A. And so B is called the inverse of the element A, and it is also denoted by A raised to the power minus one, essentially by this. So this is, note that this is not the value 1 by A, because like 1 by is only for like if we have defined division, but this is just a notation. Like this A inverse is nothing but a notation for the inverse of an element A. So this does not mean we are raising it to the power minus one in any sense, or we are saying the value 1 by A. We are just defining some notation. So yeah. So I just want to point this out. So these are the four properties uh, which, if followed, we'll call the G comma O pair to be a group. So yeah. So let me just underline these. So this is the basis of group theory, and everything we'll do will and everything discussed from here on will have the basis in this only. So one thing, like just to cover everything, like just for the sake of covering everything. So note that a group need not have commutative property. And what does that mean? That means basically A or B need not be equal to BOA in a group. So the value AOB need not be equal to the value BOA. This is what I was discussing, that AOB and BOA might be different. Like, and like, so this property is not essential for it to be called a group, but it's a nice property to have, right? If our AOB and BOA are equal, then we can sort of uh, change the order of elements also. Like in AOBOC, we can change the ordering of the elements and stuff like that. Like we do in addition or multiplication also, we can change the ordering. So this is a nice property to have, but for definition of a group, we don't need this. We don't consider this property. But if this commutative property holds, then that, if for some group this commutative property holds, then that group is called an abelian group. Maybe I'll just write this down. If a group does have commutative property, and what is commutative property? That is for any two elements A comma B in G, AOB is equal to BOA, then that group is called, like for any two elements. So basically, any two elements of G, like A and B can be equal also, or can be any two, like they can be equal, or like any pair of elements basically. AOB should be, if AOB is equal to BOA, then that group is called a billion group. So just for the sake of definitions, I just, or maybe for sake of completeness, I just want to point this out also, that this group is called an abelian group. So yeah, then that group is called an abelian group. So it's a nice property to have. So what properties does an abelian group have? So abelian group has these four properties because it's a group, and if it has it also has commutative property because yeah, we have defined it this way. So yeah, so I think we sort of now know what a group is, right? So similarly, now maybe I should also discuss what a subgroup is. So why am I sort of focusing more on the definition in this session or these preliminaries? Because once these definitions are like clear to everyone, then these problems are sort of easy to follow. So yeah. So I'm just giving you a high level idea of the definitions because after this, like these questions will be easy to do. So yeah. So what is a subgroup? So basically, a subgroup is basically like we know there is a subset of a set, right? Similarly, there is a subgroup of a group. So what is a subgroup? A subgroup of a group. So basically, if we denote so basically a subgroup is also a group. Uh, Maybe I should write it this way. A group H comma O is is called a subgroup of the group G comma O if H is a subset of G. So note that what this G was in the definition of group, this G was a set of elements, right? Similarly, here H is also a set of elements. And now what we are defining is basically this operation O remains constant in both of these groups. And what we are saying is a group H comma O. So H is basically a set of elements, and this operation O is a subgroup of the group G comma O if H is a subgroup, if H is a subset of G. So note that G and H were just subset of elements and this operation O remains the same. So we define the same operation over these elements. And if a subset of those elements also follows these four properties, then that is called a subgroup. So note that this H comma O should be a group to be called a subgroup first of all. So these four properties should actually hold. And only after that we can say that this will be a subgroup. So yeah. So one thing to note is that uh, it is easy to see that identity element is, so there's an identity element in a group, right? So identity element, if we just take the set which consists of only the identity element, then that set also follows all these four properties because identity element in itself has this existence of identity, it has invertibility, closure, and associativity. So it is easy to see that the set that the it is easy to see that basically this pair, this E comma O pair forms a subgroup of G comma O. So basically note that H is a subset of G. So the elements of H should be present in G also. So H can be also equal to G, right? Because in subset, a proper subset is something where H is not equal to G, but here we have just defined a subset. So H can also be equal to G. So note that if we take H as just this element, the identity element, then this forms a subgroup of G. And also if we take H equal to G, then that also forms the subgroup of G. If H is equal to G, then it is also a subgroup of G. So basically every group has at least two subgroups. And what are those subgroups? Those subgroups are uh, basically the identity element and that group itself. Hence, for so hence any group G comma O such, and we sort of define that the number of elements in G is greater than 1, or let's say greater than equal to 2. Because if it was just one, number of elements was just one, then it would be the identity element itself. So any group G comma O with the size of G is greater than equal to 2 has at least two subgroups. That is when H is equal to E or H is equal to G. So yeah, I just want to point this out. So yeah, so maybe now I guess we can sort of, if we are clear with the definition of what is a group, what is a subgroup, and what are these four properties, I guess we can get started out. And if we need something else, I'll just modify this along the way. So yeah. Okay. So uh yeah. So first question asks us uh, the total number of subgroups of a group G if number of elements in G is equal to 31. So okay, so maybe yeah. Uh, Maybe I should define something else also, or yeah. So maybe I should define what an order of a group is. Order of a group. So what is an order of a group? So order of a group is nothing but number of elements in G is called the order of the group G comma. So we know that G is a, so in this G comma O, G is basically set of elements. So number of elements in G is actually called the order of that group G comma O. So yeah, so this is just a definition and is like not too difficult. So yeah. So basically, what we are asking the first question is the total number of subgroups of a group G such that order of that group is 31. So basically, if the number of elements in the group is 31, then what is the total number of subgroups? So, so this is sort of, we don't know right for now. First of all, we know that since G is 31, it is greater than equal to 2. G is greater than equal to 2 because G is equal to 31. So we first of all know that it has at least two subgroups, right? Which is the identity subgroup and like this total group G itself. So we know that maybe I'll write like this. Since G is greater than 1, or maybe greater than equal to 2, uh, we know that mm, G has at least two subgroups. So we know that the number of subgroups will at least be equal to 2, right? But we want to find out the actual number of subgroups. So it is actually greater than equal to 2, but what's the actual number? That's what we want to find out. And that's where an important theorem which has been covered in the lectures comes in. So I'll just write that theorem down. It's called the Lagrange theorem. And what does Lagrange theorem say? So Lagrange theorem says that order of a subgroup H divides the order of a group G. So what does this mean? So if H is a subgroup of the group G, then order of that subgroup H should divide the order of that group G. So like order is actually nothing but an integer, right? Because it's just the number of elements in the group. So let's say H, like G said, let's say if G has 10 elements, then H can only have, let's say, one element or two elements or five elements or 10 elements, because these are the only four numbers which divide 10. So yeah, so this is a sort of an important theorem, and like its proof has been, I'll not discuss its proof because it has been covered in the lectures. So yeah, but this is an important theorem to note that order of a subgroup H divides the order of the group G. So, and how is this useful here? So note that we are given that order of the group G is 31. So since order of the group G is 31, any subgroup H of G should actually have an order, will have an order such that H divides uh, G, right? Like H, the order of that H should divide 31. So any subgroup H is should have an order which divides 31. That is 31 is divisible by H. So note that if H is a subgroup of G, then basically 31 should be divisible by this H, the order of the subgroup H. But we know that 31 is actually a prime number, right? So what's a good property of prime numbers? That there are only two numbers which divide a prime number, one and that prime number itself. So since 31 is prime, mod H, the basically order of the group H can only take the values 1 and 31. So we need that this mod H, I denote this by mod H, but it is essentially the order of the group H. So this mod H should divide 31, right? But 31 can only be divisible by two values, which are 1 and 31. So this mod H can only take two values, which are 1 and 31. And note that if mod H is equal to 1, so basically what this means is that H only has one element. And like we know that a group should have an identity element always if it is a subgroup. Uh, so it will just be this group, the group of identity element comma O. So if H is 1, then there is only one choice of H, which is so. So if order of that H is 1, then there is only one choice of H, which is nothing but the identity element. Right? Because every group should contain an identity element. And like so, and if the group has an identity element and its number of elements is only one, then it contains exactly the identity element itself and nothing more. So if H is 1, as a group should always contain the identity element E. Thus, H is nothing but equal to this set, the element E itself. So this H contains, so H is a set which contains singular element E. So if H was 1, if it can take the mod H can take the values 1 and 31. So if mod H was 1, then we know that there's only one choice of H. Similarly, if mod H is 31, if mod H is 31, then H is nothing but, so G also had 31 elements, right? And H is actually a subset of G. And if H also has 31 elements, then H is actually equal to G itself. Then it is easy to see that H is equal to G itself. So note that there are two choices for H. So if order of H was 1, then there was only one choice of H, which was this element E. If order of H was 31, then H can be equal to G only. So since these are the two choices, so we sort of have only two choices for subgroups. So what we essentially show here is that uh, uh, number of subgroups of G is actually less than equal to 2. And why is this? Because like if H was actually equal to 1, then there was one choice. If H was 31, then there was another choice. And there cannot be any more choices. So we sort of have an upper bound that number of subgroups of G is actually less than equal to 2. But we also know that G has at least two subgroups because size of G is greater than equal to 2 because we actually had this property. And we have also shown that number of subgroups is also less than equal to 2. First, we showed that it has greater than equal to 2. Then we show that it has less than equal to 2. So from these two statements, we claim that hence G has exactly two subgroups. That is H is equals to identity element and H is equal to G. So these are the only two subgroups which H has. So one thing to note is so in general a group can have multiple subgroups. But what was a special property for this group G? The special property for this group G was that its order was a prime number. So since 31 was prime, a prime only has two factors, and because of that, we were able to claim that if if the factor was actually 1, then we just have H equal to E. If factor was the number itself, then we had H equal to G. So note that if any time at any time if order of G is prime, then the number of subgroups of G will only be 2 itself. But if it is not prime, then it can be more than 2 also. So yeah, just keep this in mind. So this is the correct answer. Maybe I should just underline this. So yeah. So we are done here. So G exact has exactly two subgroups, which are H equals to E and H equals to G. So yeah. So maybe I should mention here why I did we do this. So by Lagrange theorem. So yeah. So G was 31, and by Lagrange theorem, any subgroup should have an order which divides 31. Yeah. So we are done with the first question then. Okay, so someone has joined the session. So hello Jitesh. So I was just I discussed some preliminaries, basically definition of groups and subgroups and order of a group and Lagrange theorem. And then I was just discussing the first question now. The first question is total number of subgroups of G if number of elements in G is 31. So maybe you can go through this while I start discussing the second question. And if you have some doubts in the first question, then you can ask me in chat. Like I can explain to you again. I don't have any issues with that. So if you feel you have some doubt in the first question, then I can try to explain again. Till then, maybe I can start with the second question. So, so yeah. So if you have any doubts, please type in chat. So yeah. So the second question says that the value of phi of 437, where actually this phi is actually Euler's-Taussian function, where phi is the Euler's-Taussian function is. So, so this is a very straightforward question. It is nothing new. So this has been discussed like directly in the lectures. So the question is just asking the value of phi of 437, where phi is the Euler's-Taussian function. So we need to calculate just this value, phi 437. And uh, so this has been discussed in the lectures that the value of uh, this function can be calculated very easily. And maybe I'll just show you how. So first of all, to calculate the value of this phi of n for any number n, we first of all do the prime factorization for that number. So let's just say I do the prime factorization for 437. So So we'll first need to write the prime factorization for 437. And what's the prime factorization for 437? Uh, Maybe I'll just think out now. Can be the prime factors for 437. So it would be divisible by, okay. So 437 maybe can be written as like this, 9 times 20, 19 times 23. So this is the prime factorization of 437. So maybe I should first of all define Euler-Stoichhian function. So maybe phi of n is actually equal to n minus 1. So this has been discussed in the lectures. Maybe like there are more better definitions for this function, but I'll just stick to what has been discussed in the lectures and not stray away from that. So phi of n is n minus 1 if n is prime. If n and phi of n is actually equal to uh, p minus 1 times q minus 1, if n is equals to pq, where p and q are prime. So note that if we want to calculate the value of phi of n, uh, it is if this n is prime, then this value is just equal to n minus 1. And if this n is actually equal to a product of two prime numbers, p and q, then this value phi of n is actually equal to p minus 1 times q minus 1. So there may be cases where n is not prime and not it cannot be written as this p and q also. Let's say a number 7 times 11 times 13. So it is not prime and it is not in the form of p times q, but there is a like for that also we can define the Euler-Stoichhian function, but maybe we'll not get into that. Even though it's easy, but still we'll just stick to these two cases where if n was prime or if n was equal to p times q. So phi of n is equal to p minus 1 times q minus 1 if n is pq and n minus 1 if n is prime. So what do we have here? We want to calculate the value 437. And what is 437? It is nothing but 19 times 23. So out of these two cases, actually this 437 falls in the second case, as this n, the n here is actually equal to 437, and this 437 is actually equal to 19 times 23, which are, and 19 and 23 both are prime. So 437 can be written as product of two primes, 19 and 23. So p is 19 and q is 23. So what will be the value of phi of n? It will be something like p minus 1 times q minus 1. So hence p is equals to 19 and q is equals to 23. So what does this imply? This implies that phi of 437 is equals to p minus 1 times q minus 1, where p is equals to 19 and q is equal to 23. So it will be something like 19 minus 1 times 23 minus 1. And what will this be equal to? This will be nothing but 18 times 22. And what is 18 times 22? 18 times 22 is something like 220, 440, and it will be 396. Yeah. So 396 is the correct answer. So yeah. So this was pretty easy. Like you just need to know the definition for phi of n. This has covered in the lecture. So these are the two relevant cases which you will be arriving at most of the time. And for these two cases, you just need to check what's the actual answer. So yeah, pretty easy, right? So now let's come to the third question then. Okay. So for third question, I would expect you guys to know about Diffie-Hellman key exchange, because like this has been covered in the lectures. Like if you know about it, then this problem is quite easy. So yeah. So the third question says that let G, comma O be a finite cyclic group with generator G, where the discrete log problem is. So what's a cyclic group and what's a generator of that group? This has also been covered in the lecture. So maybe I just discussed with you guys the definition of a group, a subgroup, and not of a group and Lagrange theorem. Maybe I'll not get into cyclic group and stuff also, because like it will be just like reinventing or re-telling you guys whatever has been discussed in the lectures, and I don't want to get into that much. So yeah, so let's just do this problem straight away then. So this says that let G comma O be a finite cyclic group. I'll assume that you guys know what cyclic group G, what is the cyclic group and what's the generator of that group, and like what's the discrete log problem. So this has also all been covered in the lectures. So let G comma O be a finite cyclic group with generator G where the discrete log problem is hard. So specifically, like it is hard to compute the value of G raised to power AB given G raised to power E A and G raised to the power B. So like this is what is the Diffie-Hellman exchange protocol, and this has been also discussed in the lectures. So in Diffie-Hellman exchange protocol, it's just that we are given two values, G raised to power A and G raised to power B, and like computing G raised to power AB is hard. So Diffie-Hellman exchange is based on this sort of argumentation itself, that if we are given G raised to power A and G raised to power B, it is hard to compute the value G raised to power AB. So yeah. So now the question asks us, which of the following functions are also hard to compute? So what we are essentially given is, so we are given two values, G to the power A and G to the power B. And now we want to see whether calculating some value is easy or is it hard or what else. So yeah. So we know that we are given that computing G raised to the power AB is hard. Maybe I'll just write you guys in the answer, like what essentially the problem is saying. So we are given uh, two values, G raised to the power A and G raised to the power B. So we are given these two values. We are not given what is G and what is A. We are just given these two values, G to the power A and G to the power B. Not given what is G and what is A, B. So we don't know what are A and B or what is G. Maybe we, oh, okay, sorry. We know G, but we don't know A and B. Not given what is A and not given what is B. So we are given the generator G. We are also given two values G to the power A and G to the power B, but we are not given what is A and what is B. And this is what is called a discrete log problem. Like if we are given the generator G and the value G to the power A, then we need, if we want to find out what is the value of A, that is something like a log problem in teacher sense. That's why it's called discrete log problem. And this problem is hard. Like this problem is hard to do. So yeah. So we are not given what is A and what is B. And yeah, if we were able to find out what is it, that would be solving the discrete log problem. So, and what we need to find out is, so basically, essentially the question says that we are given these values and now we want to check what values are, what values can we compute directly using G to the power A and G to the power B without knowing the values A and B. So we don't know what is A and B because if we knew, then the discrete log problem would be solved, but that is hard. So, so we just want to check if we are given G to the power A and G to the power B, what values can we compute without knowing the values A and B. So let's just check option by option. So option A is, so the option A says we want to compute the value of G raised to the power 2 times A plus B. So maybe I should mention these values as capital A and capital B to just. Yeah, so I just gave these values some name like A, capital A and capital B so that it becomes a little easy. Like I don't need to write this uh, g raised to power a and g raised to power b every time. So this is just a notation of capital A and capital B. This has nothing to do with these A and B's. So yeah. Okay. So we are given the value g to the power a and g to the power b, and now we want to see whether we can calculate this g raised to power 2 times a plus b using this. So I hope it can be seen that g to the power a plus b, here g raised to the power 2 times a plus b can just be written as g raised to the power a plus b times whole square. So what I'm trying to write here is maybe I'll just copy this. So this is nothing but g raised to the power a plus b and this whole raised to the power square. So note that squaring and multiplication are easy to do problems. We don't need the values a and b for that. We can easily square or something. So and now how can this g raised to the power a and b be computed? It can be written as g raised to the power a times g raised to the power b. So g raised to the power a. So maybe I should mention this not times, but oh. So yeah. So g raised to the power a over g raised to the power b and this whole square. So this g raised to the power 2 times a plus b can essentially be written like this also. I hope it's clear to you how it can be written. Like I've just followed the rules of exponentiation and nothing else. And now we sort of already know the value g raised to the power a and g raised to the power b, right? These values were already given to us as capital A and capital B. So it will be nothing but capital A or capital B, and we can always square easily. So it can be easily squared, and so basically, hence option A is easy to compute. So note that easy to compute in what sense? In the sense that for computing this value g raised to power 2 times a plus b, we won't need to compute the values of a and b. We won't need to find out the values of a and b. We can directly use the value g raised to power a and g raised to the power b to find out the value of g raised to power 2 times a plus b. Like if for some example, we need to find out what exactly is a and what exactly is b, then we are in trouble and we won't be able to do it directly. So yeah. So option A is easy to compute. What is option B here? Option B is g raised to the power a times b plus 1. So, what is the option here? It is something like g raised to the power a times b plus 1. And it can be written as something like g raised to the power ab plus 1, like ab plus a, because like if I just open this parentheses, and this is nothing but g raised to the power ab times like g raised to the power a, right? I have just followed this exponentiation. Okay, this autocomplete is screwing it up, but yeah. And yeah. And now we sort of already know what the g raised to the power a is. So this is something like g raised to the power ab oa. So in option B, we have sort of written it in something like g raised to the power ab times a times capital A. This capital A was already given to us. So note that. So what I'm now trying to claim is, I'll just give you an idea. So what I'm trying to claim now is that if we were able to easily compute, like we need to answer whether calculate calculating this value is easy or hard, right? We just need to see if calculating this value is easy or is it hard. So what I'll try to do is I just written down this value in terms of this, like g to the power ab times a. And now what I'll try to do is maybe see if doing this is easy or if doing this is uh, hard. So like what I'm trying to claim is if we knew that calculating this was easy, like if we were able to calculate this easily, then what I'm trying to claim is I can also calculate g raised to the power ab easily. And why is that? I'll just need to multiply this value by the value of a inverse. If I just multiply this value by a inverse, then I'll be able to obtain g raised to the power ab also easily. But we know that computing g raised to the power ab is hard. So that's why this problem should also be hard. So maybe I'll just write this down. Maybe I should write this as capitals or maybe like this one. If g raised to the power ab times a was easy to compute, so this can be sort of a claim. Maybe I should write this as a claim rather. So in this option B, my claim is that if g raised to the power ab was easy to compute, uh, then g raised to the power ab is also easy to compute. And why is that? What's the reason for this? The reason for this is uh, we can calculate like reason. Maybe I'll just write down as g raised to the power ab is nothing but g raised to the power ab times capital A times capital A inverse, right? So if we like this calculating this value was easy, if this calculating this value was easy, so to calculate g raised to the power ab, what we do is we first calculate this value and then we calculate this value. Computing inverse is also easy, and then we multiply these two values. And note that by associativity, like this can also be written as g raised to the power ab times a inverse. So this a and a inverse will cancel out, and we will only be left with g raised to the power ab. So yeah. So I hope you understand what I'm trying to say here. So what I'm trying to just say here is that if we were able to calculate this a, we can find out this a inverse easily. And if we were able to find out this also easily, then we can just multiply these two values and I'll obtain g raised to the power ab also easily. But we know that uh, calculating this is hard. This is already given to us. So that's why calculating this should also be hard. So yes. So if g raised to the power ab was hard, if g raised to the power ab times a was easy, then we could calculate g raised to the power ab easily by computing g raised to the power ab times a and multiplying. Let's say I'm just saying multiplying, but by multiplying what I mean is actually taking this operation with a. So yeah. So sometimes a lot of people in groups theory just denote this operation as multiplication, but note that this is not the standard multiplication. It can mean multiplication in other senses also. So yeah, and multiplying it by A inverse. So we know that if this was easy to compute, then this is also easy to compute. But we know that this is not easy, right? Hence, by contradiction, we can say that g raised to power ab times a is hard to compute because like if this was easy, then g raised to power ab will also be easy. But we know in Diffie-Hellman that this is not the case. So that's why g raised to power ab times a is also hard to compute if g raised to power ab was hard. So yeah. So that's why this is actually hard to compute. So maybe I should uh, underline this, or maybe this underline hard to compute part. Right. So that's why option B is hard to compute. Now let's come to option C. So Jitesh, I hope everything is clear to you till now. Like if you have any doubts, like I said, you can ask me in chat anytime. I'll try to explain it to best of my capabilities. So yeah. Okay, sure. There are no doubts. Nice. So again, in option three, we have something like g raised to the power a plus 3 times b. So option C is something like uh, g raised to the power a plus 3 times b. And this can again, this is somewhat similar to option B. So this can again be expanded as g raised to the power ab plus 3b. And this can again be written as g raised to the power ab times g raised to the power 3b. So which is nothing but g raised to the power ab times. Okay, I need to copy this symbol. G raised to the power ab times this g raised to the power 3b is nothing but g raised to the power b raised to the power 3. So it is something like b cube, right? So option C is something like this, g raised to the power ab times b cube. So note that we are already given b. Computing b cube is easy. And so computing b raised to the power minus 3 is also easy. So if calculating this value was easy, then we could just multiply it by b raised to the power minus 3, and then we would arrive at g raised to the power ab. So uh, I'll just write down, I'll not write down everything like I did here, but I'll just write down similar to option B, we can write g raised to the power a plus 3b equal to this value times b raised to the power minus 3. So, so yeah, and hence option C is hard to compute. So same like the argumentation will be same as the given in option B. So like similar to option B, we can write, and hence option C will also be hard to compute. Why did I write just compete? Not compete, but compute. So yeah. So similarly, we are given this option D. Option D is something like G raised to the power. This symbol, upward arrow symbol, is generally used for powers. So this is something like G raised to the power A square B. So I wrote this as power because like you can't do a superscript of a superscript in docs, right? That's why I wrote it as something like this. But what you should read it as is G raised to the power A square B. So in power, the term is A square B actually. So we sort of want to see whether we can calculate this G raised to the power A square B or we can't calculate this A square B. So like by similar reasoning like option B, like the reasoning provided in option B and C. So note that generally the values which will be easy to compute if we are given G raised to the power A and G raised to the power B will be terms of the form let's say G raised to the power A plus 2B, A plus 3B, or let's say G raised to the power linear combination of A and B. Because then we could just multiply G raised to the power A times G raised to the power 2B to obtain like G raised to the power A plus 2B and so on. But for these sorts of values which are not linear combinations of A and B in the exponents, we won't be able to compute those using uh, just G raised to the power A and G raised to the power B. So similarly here, like if we write it as G raised to the power A square B, it will be something like G raised to the power AB raised to the power A. And we already don't know A, and we also know that G raised to the power AB computation is also hard. So computing this value will also be hard. So this is also hard to compute. So I'm not writing everything down here properly, but I hope you get the idea, like from option B and option C. And like option A was easy to compute because it was a linear combination of A and B in the past. But here, if we had this AB term in the exponent, then it was hard to compute. And here we have something like A square B term in the exponent. So this is also something which is hard to do. So this is also hard to compute. So yeah. Just writing out the options. So the question was which of the following options are hard to compute over G? So options B, C, and D, B, C, and D are hard to compute. This is the final answer. So yeah. So now I hope this is clear. So then maybe we can move on to the fourth question. So fourth question is a very straightforward question. Like it's just directly from it's an information based question. So I'll just do this fast because like if you if you don't know, if you guys don't know what is Diffie-Hellman key exchange or what is L-Gamal crypto system or something, I'll not discuss this in the in this session because like these are stuff which have been discussed in the lectures, so you should probably see the lectures instead. So yeah. Maybe we can get started with just the question. So yeah. So the security of the RSA crypto system depends on how the prime numbers P and Q are chosen. So let's just do option by option. We just need to find out which of the following statements are incorrect. So let's just do option by option. So option A. So the security of the RSA crypto system depends on how the prime numbers P and Q are chosen. So this has directly been discussed in the lectures. Like in RSA crypto system, we find out two prime numbers P and Q. And like security depends on how prime numbers P and Q are chosen because like if we just choose a prime number P and Q as let's say 2 and 2 itself, then RSA will be very easy to solve. The RSA crypto system will be broken down if these prime numbers are not chosen wisely. Like this has been discussed in the lecture, so you can see this. So this is correct as discussed. So all these four statements are actually some statements which have been discussed in the lectures and are information based rather than, or maybe not exactly information based. There is some logic behind it, but the logic has already been discussed in the lectures. Nothing new here. So I just wanted to put this question to get you guys to watch the lectures and sort of Note the important properties of different crypto system. So RSA crypto system can be broken if the order of Z star n is known. So this is actually also correct. And you can again see this from the lectures. Yeah. So option C says in that diff. So this DH is nothing but Diffie Hellman. So DH, Diffie Hellman, the Diffie Hellman key exchange. The key obtained at the end is G raised to the power alpha plus beta, where alpha is chosen by one of the parties and beta is chosen by the other party. So this is actually incorrect. In Diffie-Hellman, actually, we don't create the key G raised to the power alpha plus beta, but rather we create the key G raised to the power alpha times beta. Like as we had seen in this third question also, the main reasoning for Diffie-Hellman is that compute this G raised to the power AB is hard to compute. So that's why this is what the key is. If we had just given G raised to the power A plus B, then that would be actually easy to compute. So Diffie-Hellman would fail if we just do something like G raised to the power A plus B. That's why we take something like G raised to the power AB in Diffie-Hellman key exchange. So yeah. So that's why this statement is incorrect, as the key obtained at the end in DH key exchange is actually G raised to the power alpha times beta. Yeah. G raised to the power alpha times beta. So yeah. And now let's go to option D. So option D says L-Gamal crypto system can be broken if alpha is known. So you can just see what L-Gamal crypto system is in on the lectures, and like, yeah, if alpha is actually known, then this crypto system also breaks down. Correct. As discussed in the lectures. Yeah. So now let's come to the fifth question then. So fifth question is so this question, like this fourth question was nothing but just direct statement from the lecture. So yeah. So we just might need to find out which of the following statements are incorrect. So A, B, and D are correct. So the only incorrect statement is actually option C. It's option C. What is that? Hence, option C is actually incorrect. So option C is actually the correct answer for this question, because we need to find out the incorrect statement. So yeah. So always keep this sort of thing in mind, like what the question is asking while answering. This question was asking actually the incorrect statement. So someone might, if they just mark the correct statement, then that would have resulted in like option A, B, and D. So even though your thinking might have been correct, but you finally would not have got the marks for the same. Like, it's not a quiz, but yeah, in the quiz, if something like this happens, so that's why just keep an eye on the question, like what it's asking. So here, like option C is the correct answer in this question. So yeah. So maybe let's come to question 5 then. So, okay, so we have defined this group, subgroups. Now let's just come to this question 5. So what is this question 5? So question 5 says, let G be a cyclic group with a generator G, whose order is 32. So then which of the following are true about G? So the question is nothing but like G is given as a cyclic group to us, and the generator of that cyclic group is this small g. So since we have time, maybe I'll just discuss with you on a high level, like what a cyclic group G is or what's a generator. So generator of a group is nothing but if G is a generator of a cyclic group, then what that means is that we can obtain all the elements of that group capital G by taking powers of this generator small g. So we do something like if we take the element g, we take g square, we take g cube, we take g to the power 4, g to the power 5, and so on. Then we'll actually obtain all the elements of this cyclic group. And the order of the generator is actually nothing but like this uh, the order of a generator is nothing but the smallest power, uh, like the order. Maybe I should write it like here only, the definitions. So we know what is an order of a group, right? Order of a group is nothing but the number of elements in the group. And so there's another thing which is similar to order, which is order of a gen, or maybe order of uh, an element G of a group, capital G. So note that where put it? So order of a group is nothing but number of elements under group, right? Then there is another definition. This has also been covered in the lectures, but yeah. So we associate order to a group, but we also associate order to an every element of a group. Like order of an element small g of a group capital G. So if we take any element small g of a group capital G, then we have also have a definition for order of that element G. So this was the order of the group capital G. And now we also have a definition about order of an element small g of that group capital G. And what is this order? This is nothing but the smallest positive integer n such that g raised to the power n is e, where e is the identity of group G. So, like order of the element G is like quite simple definition. The smallest positive integer n such that this G raised to the power n is actually equal to the identity element of that group. So if we just this G raised to the power n means like multiplying G n times. So if we first take the term G, then take G square, then G cube, then G to the power 4. So the first time at which we arrive at the element E, where E is the identity, then at that moment we'll call it as the order of that element small g. So this is sort of a definition for order of an element for group G. So if we are clear with this definition, then maybe we can proceed with the problem. So now in a cyclic group, the property of a cyclic group is actually it has an element G, which is called the generator of a cyclic group. And this generator has a property that the order of the group, is nothing but the number of elements, right? And this generator G has a property that if we take the sum G square, G cube till like, let's say the order of, and if we take the sum G square, G cube, G to the power 4 and so on, we'll obtain all the elements of this capital G. So actually, what I essentially mean to say, so here the generator G has an order 32. Note that here, like G is a cyclic group and the generator G has the order 32. So basically 32 is the smallest number at which like G raised to power 32 is actually equal to the identity element of the group. So G raised to power 32 is actually identity element and G raised to power 33 will actually be again equal to this G only because identity times G will be nothing but G itself. So the order of a generator of a cyclic group is actually equal to order of group itself. Note that order of a, maybe you can refer to lectures also. This is a part of lectures also. So, but I just want to point this out here also. Order of a generator G of a cyclic group is actually equal to order of the cyclic group. So if G is a cyclic group and small g is a generator, then order of that generator G is actually equal to order of that group G also. So what I mean by that, here we are given that order of the generator G is 32. So 32 is the smallest power at which G raised to power 32 is actually equal to 1. And so what we essentially have is that order of the cyclic group is also 32. So this means that this cyclic group capital G actually has 32 elements. Since order of generator G is 32 given, hence order of cyclic group is also 32. So hence G is also 32. So this is something like which I don't think is useful for this question because this question has something else. But I just want to point out that maybe one option could have been like this, like instead of let's say none of the given options, mod G is equals to 32. So let's say this is the fourth option. So what I mean to say is this option D will also be correct here. Right? Order of a generator G of cyclic group is actually order of the cyclic group capital G. But note that this is not the question. I just want to point this out. So yeah. So we know that for a generator G, like G raised to power 32 is the smallest value at which its C value is equal to small e, which is the identity element. So since order of G is equals to 32, hence n equals to 32 is the smallest value such that G raised to the power n is equals to E. So essentially what we mean is nothing but G raised to the power 32 is actually equal to E, right? N equal to 32, but another thing which this implies is G raised to the power 32 is actually equal to the identity element E. Otherwise, so yeah, so G raised to the power 32 is the smallest element at which it is equal to identity element E. I guess this much is pretty clear because this is by definition only. Like this was the definition of order of an element. So now maybe we can do option by option. So this is one thing which we need to keep in mind. Like this property is what we need to keep in mind. And now we can sort of proceed with the questions. So only the element G raised to power 8, 16, and 24 are of order 4. So now sort of first of all, one observation which we need to make here is this has been discussed in the lectures also. So G raised to the power 32 is the smallest value at which it takes the value E. So what this means is that G square, G cube, G to the power 4 till the value G to the power 32 are all different from each other. Also, the values G comma G square comma G cube till let's say this G to the power 32 are all distinct from each other. So this is also property of G because if two values were equal, let's say G square and G to the power 10 were equal, it would mean something like G raised to the power 8 is 1 because we could multiply G both sides by G to the power minus 2. But we know that G to the power 32 is the smallest value at which G to the power 32 is 1. So that's why these values g, g squared, g cubed till g to the power 32 are all distinct from each other. So this is also like from the lectures only, nothing new. So why is this important? Like, so these two claims are actually very important to us. This g to the power 32 is actually equal to e, or I refer to e as sometimes 1 also, because if we take multiplication, then in multiplication identity is 1 actually. So g to the power 32 is actually equal to e, and also g, g squared, g cubed till g to the power 32 are all distinct from each other. So these are two important things. And now the option A says that only the element g to the power 8, 16, and 24 are of order 4. Now we want to find out what elements have order 4. So what does having order 4 mean? It would mean something like an element x would have an order 4 if x to the power 4 is actually equal to e, and 4 is the smallest number at which this x to the power n actually comes equal to e. So uh, it can be actually sort of seen easily that uh, g to the power 8 will have order 4. So to verify whether only these elements have the order 4, we'll need to check whether if these indeed have order 4, and we also need to say whether any other element won't have order 4. So the option says only the element g to the power 8, g to the power 16, and g to the power 24 are of order 4. So to verify this option, we need to do two things. We need to verify whether these three elements have order 4, and we also need to show that no other element will have order 4, right? Only then can we say that only these elements are of order 4. So here we'll need to show that g to the power 8, g to the power 16, and g to the power 24 have order 4, and no other element of g can have order 4, right? And how will we do this? So for doing this, maybe we can do this in uh, two steps, maybe. So the first step will be uh, showing that these have order 4. And how do we do this? So it's sort of uh, easy to see that. Okay, maybe let me just think about it a minute. Maybe we can have a better approach than what I had in my mind initially. So um, if something has an order 4, then what does this mean? This means that so yeah, so I think there's a better way to show this. Uh, so so yeah. So we'll sort of need to show that these have order 4 and no other element can have order 4. So instead of this, what I'll show is uh consider any element G prime such that uh, G prime has order 4. Now, what will this mean? This will mean that uh, thus G prime raised to the power 4 is actually equal to E. Also, as G is a generator, so G prime can actually be written as G raised to the power something, right? G raised to the power A. Because generator is something such that like every element of the group can be written as some power of that generator for some A. So if we consider any element G prime such that G prime has order 4, then we first know that this property holds true that G prime raised to the power 4 is E, and also G prime is G raised to the power A for some A. So what this essentially means is that thus G prime raised to the power 4 is actually equal to E, and E was actually equal to G raised to the power 32, as we had already given, as you are already given. And what does this imply? This implies that G prime was actually also equal to G raised to the power A. So this will be something like G raised to the power A raised to the power 4 is actually equal to G raised to the power 32. So what does this mean? This means that G raised to the power 4A is actually G raised to the power 32. So note that one intuition might just be to like cancel these G and just say 4A equals to 32. But note that this is not correct because uh, since this is something like a cyclic group. So what do I mean by this? So this can also be written as, instead of G to the power 32, it can also be written as G to the power 64. It can also be written as G to the power 96 and like so on. So it can be written as 32, 64, 96, 128 and so on. So this does not mean like you can just cancel these G's and find out that 4 equal 32. You'll actually need to solve the system. You'll actually obtain multiple values of A. Like sometimes you'll just say G to the power, if 4A is equal to 32, you'll obtain one value of A. If 4A equal to 64, you'll obtain another value. If 4A equal to 96, you'll obtain another value and so on. And so, uh, so basically, if we take 4, so if so 4A equal to 32, comma 4A equal to 64, comma 4A equals to 96, comma 4A equal to 128, and so on, are the possible values of A. And what do we get from here? So from 4A equal to 32, we get A equals to 8, A equals to 8. Then we get A equals to 16. Then we get A equals to 24. And after this, for A equal to 128, we get something like A equals to 32. And note that if A was actually equal to 32, we just obtained if A was actually equal to 32, we'll just obtain the number G G raised to the power 32. Like G prime would actually be equal to G raised to the power 32 itself. And maybe I should just write it down first of all. Yeah. 32. So it just forms something like 8, 16, 24, 32, and so on. So basically, this implies that A equals to 8, 16, 24, 32, 40, and like this series going to infinity are possible solutions for it. Note that these are not like, or maybe we can write like, yeah, are possible values of A. And why am I saying these are possible values? Because I have used this property that G prime equal to G raised to the power A and equated something like this, that G prime raised to the power 4 is equals to E is equal to G raised to the power 32. But I also need to ensure for G prime to have an order 4 that G prime square and G prime cube, like if G prime should have order 4, then 4 should be the smallest value at which G prime raised to the power 4 has is equal to E. So like G prime should not be equal to E, G prime square should not be equal to E. Similarly, G prime cube should not be equal to E. And G prime raised to the power 4 should be the first value at which it comes out equal to E. So from these values, like, so note that values after 32 are essentially useless because g raised to power 32 is essentially E. So g raised to power 40 will be nothing but g raised to power 8 itself. So these are the four main cases for us. As g to the power 32 is equal to E, thus possible values of g prime uh, yeah, possible values of g prime are g raised to the power 8, g raised to the power 16, g raised to the power 30, g raised to the power 24, and g raised to the power 32. Uh, we still need to verify whether uh, hmm, uh, g prime has order 4. Right. So till now we have only used this equation that g prime raised to the power 4 is E, but we have not used the fact that this should also have order 4. So we note that uh, so it can be seen that uh, if we consider g prime as g raised to power 8, then the three values which we'll obtain are if we do something like g prime. So maybe I should just write down if g prime is equals to g raised to power 8. What does this mean? Uh, this means that uh, the set of, let's say, g prime squared, g prime squared, g prime cube, mhm, and this g prime is so 4 should be the so g prime raised to the power 4, we know already that it should be equal to E because that is what we have already established. So we sort of need to say that uh, this set of g prime squared, and g prime cube should not contain the value E, right? So we still need to verify whether, maybe I should mention this here. We still need to verify whether g prime has order 4. And what does this mean? Well, this means that that is any of g prime square, g prime cube should not be equal to this E, the identity of the group. So if we take, so these are the possible values for g prime, and we'll just verify for all these possible values if this holds true. Like if this g prime square, and g prime cube are not equal to E. So, and how will we do this? So this set will be nothing but g prime can be written as, can be replaced by g raised to the power 8, as we have considered g prime as g raised to the power 8. So it will be something like g raised to the power 8, then g raised to the power 16, then g raised to the power 24. And we sort of know that uh, g raised to the power 32 is the smallest value at which it is equal to E. And all these values are like smaller than 32. So all these values are actually not equal to E. Not equal to E, as g to the power 32 is the smallest value, is the smallest n such that g to the power n is E. So we are sort of done. So for g prime equal to g to the power 8, hence g to the power 8 has order 4. Now we again consider the case, like I'll just copy this and paste this for g to the power 16. And similarly for other cases, like I'll just be copy pasting for now. and I'll just change the values and we'll see whether all these fall. So we verified that it has order 4. Now we'll go for g to the power 16. So g to the power 16 will be nothing but g raised to the power 16, comma g raised to the power 32, comma uh, g raised to the power 16, 32, and 48. Right. So now we know that here that g raised to the power 32 term comes in, and this sort of term sort of already has an order of this already has the value e, right? That's why g to the power 16 does not have order 4. Mm, mm. As g raised to the power 32 is equal to e, hence g to the power 16 actually has an order of 2, actually, because g to the power 16 raised to the power 2 is actually 1. So this has actually order of 1, has order of 2. So it does not, g to the power 16 is not true. Like g to the power 8 has order 4, g to the power 16 has order 2. Similarly, if we take g raised to the power, if 24, if we take g raised to the power 24, it will be something like 24, 48, and then 72. And we know that g raised to the power 32 is actually equal to e. So we can just take like modulo 32 in the exponents, right? Which is nothing but like something like g to the 24 and then 16. And then like modulo, this will be again g to the power 8. Like module, I'm just taking modulo 32 because g to the power 32 is essentially equal to e. And now we know that all these are not equal to e, as g to the power 32 is the smallest. So hence g to the power 24 actually has order 4. So that is correct. And if g prime had actually g to the power 32, then we sort of already know that this is something like g to the power 32, something like g to the power 64, then g to the power 96. And we sort of already know that g to the power 32 is already equal to 1. So order is actually 1 itself here, because g raised to the power 32 raised to the power 1 is already equal to e. So g raised to the power 32 is actually has order 1. So from this, what do we get? We get that only g to the power 8 and g to the power 24 had order 4. G to the power 16 and g to the power 32 did not. So now similarly, g to the power 40 will essentially be g to the power 8 only, because we can take modulo 8, modulo 32 in the past. So what does this mean? This means that hence only g to the 8 and g to the 24 have order 4. So here the options were g to the power 8, 16, and 24. So this option was incorrect because g to the power 16 actually we saw had an order of 2. Hence, option A is incorrect. Right? So option A is actually incorrect. Similarly, option B is there exists no elements of order 6 and no elements of order 10. So one thing to note, like instead of getting into this, I'll just like to uh, point you guys out to the fact that you can verify this easily also, that order of any element should actually divide the order of the group. So an important property to note is this is an important property to note, I guess. Property that order of any element. So this has also been discussed in the lectures. So this property is also discussed in the lectures. So I'll not provide a proof for this. Order of any element of G should divide the order of G. So what does this mean? So order of any element of this group G should actually divide 32. So order of any element should divide 32, right? So for any, so note that the order of G we know is 32, as we earlier discussed. So in option B, we want to find out the elements of order 6 and elements of order 10. So we sort of already know that order of an element, like if order of an element should divide the order of the group, and order of the group is 32. Since 6 does not divide 32 and 10 does not divide 32, so that's why like there exists no elements of order 6 and no elements of order 10. So that's why option B is sort of correct. Option B, as 6 and 10 do not divide 32, hence option B is correct. Similarly, in option C says there are exactly 6 elements of order 7. So since 7 does not divide 32, uh, again, this statement is actually wrong because there are no elements of order 7 because 7 does not divide 32. So as 7 does not divide 32, option C is incorrect. Now let's come to option D then. So option D says like G is equal to 32, which I already discussed. Like G is 32. So yeah, option D correct as already discussed. Okay, so we know that option A was incorrect, option B was correct, C was incorrect, D was correct. So we want to find out which of the following are true. So statements B and D are true. So hence option A, comma D is the correct answer. I just underline this. So yeah. So you might feel that this has become a bit hodgepodge in the answer, like in this option A. But note that these are the two important properties which we use. Like this order is 32, and then this property at orders to divide the order of 32. And we also sort of use the definition of. So here there was nothing new. We just use the basic definition of what is actually an order of a generator and stuff like that. So these were the three things which we essentially used to arrive at everything. Everything else was just maths, pure maths. So yeah. Okay, so this was the last question which I wanted to discuss for today. So I guess this is the fifth. So yeah, this was the fifth question, and I have nothing to add from my side. So Jitesh, if you have any doubts in this fifth question or like any of the previous questions which I discussed, since we have I guess 3-4 minutes left, you can ask me if you have any doubts left, or like if you don't have any, then maybe we can close the session. So okay, so Jitesh is asking, can you show an example of El-Gamal encryption scheme and RSA with small numbers as examples? So Jitesh, I would rather have you watch the lectures instead, because like just showing an example won't introduce you to the whole theory of that. So I would recommend you should rather watch the lectures of on the NPTEL. So these El-Gamal encryption scheme and RSA scheme have already been discussed in the lectures. So I would recommend you to watch that. Okay then. So, so if you have no more doubts, then I guess you can leave, and I can sort of close the session if you have no more doubts. So okay then. Thanks. So no doubts. So thank you for joining Zitesh. Then I close the session, and we'll see you next week, hopefully in the same time slot, 6 to 8. So yeah. So bye bye and take care.